So far in the course, we've studied patterns and symmetries in the plane. In the final two geometry units, we're going to move up to 3 dimensions, and we'll find some interesting new features. The sculptures in this gallery are by the American artist Sol LeWitt, but most of the shapes in his sculptures are just a little bit too complicated for us to study at the moment. But we can explore the symmetries of these 5 very special solids. They're called the regular solids because every face is exactly the same shape and size and is connected to the neighbouring faces in exactly the same way. By the end of this video band, you'll have classified the direct symmetry groups of each of these 5 solids. Before we do that, let's just recap how each of the 5 regular solids is constructed. The simplest possible face for a solid is an equilateral triangle. You can give it 3 neighbours, which must also be equilateral triangles, and if you lift these 3 up, you can join them up to form the simplest regular solid, a tetrahedron. If you start again with this net of 8 equilateral triangles, you get the next regular solid, the octahedron. If you start with this net of 20 equilateral triangles, you get another regular solid, the icosahedron. Instead of an equilateral triangle, you could start with the next simplest regular polygon, a square. You can give it 4 neighbours, you can lift them up, 1 more square at the top, and you have a cube. The next simplest face is a pentagon. When you join 12 of these together, you get the last regular solid, the dodecahedron.
Now, although there are 5 regular solids, we shan't need to look at all of them in detail. We can save ourselves a lot of unnecessary work by considering just 3 of them. The reason for this is a curious relationship called duality, which holds between the cube and the octahedron, and also between the dodecahedron and the icosahedron.
This is how it works. Let's start with a cube and mark the centre of each of the 6 faces. Now, if you join each of these 6 points to its 4 nearest neighbours, that produces an octahedron, and clearly it's a regular octahedron. The remarkable thing is that this works in the opposite direction too. If you take the octahedron and mark the centre of each of the 8 faces, and then join each of the centres to its 3 nearest neighbours, you get back to the cube again. We say that the cube and the octahedron are dual to each other. Given any cube, there is an associated octahedron, and vice versa. Any symmetry of one is automatically a symmetry of the other, because of the way they're locked together. This gives us our first important labour-saving result. The direct symmetry group of the octahedron is the same as that of the cube, and so we need only consider one of them. We'll look at the cube. In precisely the same way, there's a duality between the dodecahedron and the icosahedron. If you mark the centres of each of the 12 faces of the dodecahedron and join each to its neighbours, well, you get a solid that certainly looks like an icosahedron. But how can you be sure? Since the dodecahedron has 12 faces, we shall get a solid with 12 vertices. If we look at the vertices of the dodecahedron, we see that each vertex belongs to 3 faces. And so in the dual, each face will have 3 vertices, and the faces will all be equilateral triangles. How many faces are there? Well, each face corresponds to a vertex of the dodecahedron, and so there must be 20 faces in all. So the dual of the dodecahedron is an icosahedron. And the converse also applies. If you mark the center of each face of the icosahedron and join them together, and you get back to the dodecahedron. So any symmetry of the dodecahedron is automatically a symmetry of the icosahedron, and vice versa. This leads to our second labor-saving result. The direct symmetry group of the dodecahedron is the same as that of the icosahedron, and so we need only consider one of them. We look at the dodecahedron. That leaves one solid remaining. What is the dual of a tetrahedron? Stop the tape and try it for yourself. You should have found that if you mark the centers of each face and join them together, then you get a tetrahedron again. The tetrahedron is its own dual.
Well, the upshot of all this is that we only need to investigate the symmetries of three of the regular solids: the tetrahedron, the cube, and the dodecahedron. In the pre-video section, you worked out for yourself the direct symmetry group of the tetrahedron. So, in the rest of the video, we're going to investigate the cube and the dodecahedron. Let's look at the cube first. We'll construct a complete listing of the direct symmetry group of the cube by cycle type. Every element of this group is a rotation of the cube. We'll make a table of the different types of symmetry, listing their various properties: the axis of rotation, the angle, the order, and the number of symmetries of any type. The first symmetry to note is the identity. Its angle of rotation is 0, and it's of order 1. And there's only one identity symmetry. Now let's look for different types of axes. Well, the first obvious non-trivial axis of symmetry passes through the centers of pairs of opposite faces. What are the possible angles of rotation? Well, here's one rotation through plus pi by 2. Here's one through minus pi by 2, and one through pi. The 6 faces occur as 3 opposite pairs, so there are 3 different axes of rotation. The rotations through plus or minus pi by 2 are both of order 4, and there are 6 of them, 2 for each axis of rotation. But the rotation through pi is of order 2, and there are only 3 of those. There are also rotation axes which pass through the midpoints of opposite pairs of edges. So there's only one possible angle of rotation here, pi. And there are 6 different axes of rotation. So the rotation is of order 2, and there are 6 of them. And these are not all. There is one remaining kind of rotation axis. Stop the tape and find the remaining type, and count how many such axes there are. You should have found that the remaining type of rotation is about a diagonal joining pairs of opposite vertices. The angles of rotation are plus 2 pi by 3 and minus 2 pi by 3. These rotations are of order 3, and there are 8 of them. In fact, we've now found all the possible types of axis of rotation for the cube. You can see why in the video notes.
So now we know what the various axes of rotation are, but we still need a way of specifying the individual rotations. Suppose we start by labeling the vertices of the cube. Well, the cube has 8 vertices, and so it's tempting simply to number them as 1 to 8, and then to describe any rotation as a permutation of these symbols. But then it soon becomes very tedious to work out the cycle notations for all the possible rotations. It turns out that there is a labeling that reduces the number of symbols we have to deal with. In fact, we can get away with just 4 distinct labels.
Let's start by labeling one face 1, 2, 3, 4. Now, we're going to try and label all the other vertices with 1, 2, 3 or 4 in such a way that each face has all 4 numbers on its vertices. Let's try and label this vertex. It can't be a 1 or a 2 because it's on this face. And it can't be a 2 or a 3 because it's on this face. And so it must be labeled 4. And once you've labeled this vertex, that fixes the labels for all the others. There is only one way of completing the labeling of the cube. But there's more to this than meets the eye. If you join the 2 red vertices, you get a diagonal of the cube. And the same is true of the 2 blue vertices, and also the green vertices and the yellow vertices. So what this means is that we've associated each of the symbols 1 to 4 with a diagonal of the cube. You'll see that any rotational symmetry of the cube leads to a unique permutation of these diagonals. And so we can distinguish the distinct symmetries of the cube by looking at what they do to the 4 diagonals. It's important to observe that any symmetry of the cube is bound to send diagonals to diagonals. And so, if you know where one vertex moves to, you automatically know what happens to the other end of the diagonal. Let's now go back to the table of the symmetries of the cube. Instead of giving just the order, we'll now give the cycle type of the permutation. Since 2 permutations of different cycle types cannot be conjugate to one another, we know that they must correspond to essentially distinct geometric operations. First, let's deal with the identity E, which doesn't permute the diagonals at all. Its cycle type is just 1. To see what's going on in the other cases, we'll use an opaque cube, and we'll concentrate on just the vertices we can see when we're looking straight down the axis of rotation. The first type of rotation has its axis through the centers of opposite faces. What happens to the labels if we rotate through pi/2 about the axis? The vertex labelled 1 moves round to where 2 was, and the vertex labelled 2 moves to 3, and so on. This gives the permutation 1, 2, 3, 4, a 4 cycle. The next type of rotation has the same axis, but this time the angle of rotation is pi. How does this permute the vertices? This time we get a pair of 2 cycles. Next, we come to axes which pass through midpoints of opposite edges. This rotation is simply the permutation 1, 2. The final type of axis passes through opposite vertices and rotates through 2 pi/3. What's the permutation this time? Stop the tape and work it out for yourself. You should have found that you can describe this rotation as the 3 cycle 2, 4, 3. So what is the symmetry group? Since it involves permutations on 4 symbols, it must be a subgroup of S4. But we found 24 elements, and 24 is the order of S4. And so the direct symmetry group of the cube is isomorphic to S4. Well, that completes our discussion of the cube. Stop the tape and make sure you've understood our argument before we move on to investigate the rotation group of the dodecahedron.
In this final part of the video, we're going to investigate the direct symmetry group of the dodecahedron. As before, we'll construct a complete listing of all its direct symmetries by cycle type. Now, the dodecahedron is the most complicated shape we have to deal with, and yet in many ways it's the most interesting. So just as we did for the cube, let's make a start by looking at all the different types of rotation which form the direct symmetry group and list them in a table. Again, the identity has angle of rotation 0 and order 1, and it's unique in the group. As with the cube, the first obvious type of axis passes through the centres of opposite faces. About any such axis, there are 4 non-trivial rotations, through plus 2 pi by 5 and 4 pi by 5, and also through the corresponding negative angles. The 12 faces occur in 6 opposite pairs, so there are 6 such axes. The rotations through 2 pi by 5 are of order 5, and there are 12 of those, 2 for each axis. The rotations through 4 pi by 5 are also of order 5, and again there are 12 of them. The next type of axis is that joining the midpoints of a pair of opposite edges. The angle of rotation is pi. There are 30 edges altogether, giving 15 axes. These rotations have order 2, and there are 15 of them, 1 for each possible axis. So far, we've found 39 non-trivial rotations, and of course the identity. Is there another type of axis that we haven't yet covered? Stop the tape and check this for yourself. There is one remaining type of axis, and, just as for the cube, it passes through a pair of opposite vertices. The angles of rotation are plus 2 pi by 3 and minus 2 pi by 3. The 20 vertices occur in 10 opposite pairs, and so there are 10 axes of this type. All these rotations are of order 3, and there are 20 of them, 2 for each possible axis. In fact, we've now found all the 60 possible rotational symmetries of the dodecahedron. You'll see why in the video notes.
To distinguish the various types of symmetry, we shall need a notation for each of these rotations. But if we give a different label to each vertex of the dodecahedron, we shall find ourselves with permutations on 20 symbols. So the first thing we need to do is to reduce the number of symbols we have to deal with.
As with the cube, we start numbering the vertices of one face as follows. Once again, we wish to extend this labeling to every vertex in such a way that each face contains the numbers 1, 2, 3, 4, and 5. Now this time, there are 2 possible ways to complete the labeling. For example, we can label this vertex as either a 5 or as a 4, but nothing else. This gives an immediate choice between 2 options. However, once we've made the choice, the rest of the labeling is completely determined. Fortunately, it really doesn't matter which labeling we choose to work with, as long as we're consistent. So we'll work with this labeling. Something rather wonderful appears when we consider the vertices which now carry the same label. If we join up the 4 red vertices, we get a regular tetrahedron. And similarly, the blue vertices form another regular tetrahedron, the green vertices, the yellow vertices, and the white vertices. So there are 5 tetrahedra sitting inside the dodecahedron. Whenever you rotate the dodecahedron, any one of these tetrahedra is sent to one of the others. So we can now use the permutations of the tetrahedra to describe the symmetries of the dodecahedron algebraically. As we did with the cube, instead of giving just the order of the permutation in our table, we'll now give the cycle type. Firstly, the identity doesn't permute the symbols at all, and so its cycle type is just 1. To work out the other cases, we look straight along the axis of rotation, and we'll concentrate on what happens to the vertices we can see when the dodecahedron is opaque. The first non-trivial type of axis passes through the centers of a pair of opposite faces. The angle of rotation is 2 pi over 5. So what is the permutation of the 5 labels? The 5 corners of the front face move round in a cycle, giving the permutation 1, 2, 3, 4, 5. What about the rotation through 4 pi over 5 about the same axis? What's the permutation this time? Well, this time the vertices move along 2 places, giving the permutation 1, 3, 5, 2, 4. Now what about the rotation about an axis through the midpoints of opposite edges? Well, the only possible angle of rotation is pi. So what's the permutation? You get the pair of 2 cycles, 1, 2, 4, 5. Lastly, there are the axes passing through a pair of opposite vertices. The angle of rotation is 2 pi by 3. Stop the tape and work out what the permutation is. You should have found that you get the permutation 2, 5, 3. There are no other types of rotation. We found all the direct symmetries, which, in the case of the dodecahedron, correspond precisely to the even permutations. So what is the symmetry group? Since it involves even permutations on 5 symbols, it must be a subgroup of A5. But we found 60 elements, and 60 is the order of A5. And so the direct symmetry group of the dodecahedron is isomorphic to A5.
That completes our investigation of the direct symmetries of the regular solids. From your pre-video work, you know that the rotation group of the tetrahedron is isomorphic to A4. In an earlier section of the video, we showed that the direct symmetry group of the cube is isomorphic to S4. And by the property of duality of the cube and the octahedron, their rotation groups must be the same. In the last section of the video, we showed that the direct symmetry group of the dodecahedron is isomorphic to A5. And by the duality of the dodecahedron and icosahedron, their rotation groups are the same. So we've achieved our aim of classifying the direct symmetry groups for all 5 regular solids.